Hi everyone, this is EmacsConf 2024. I'm Colin, and today I'll be talking about transducers. After introducing them, I'll share a bit of history about transducers and the problems that they solve, some basics about how we can use them, how they work, like how they're implemented, some demonstrations of how we can actually use them in the wild, and then some other discussions about issues that they have. Okay, let's get right in. What are transducers? Transducers are a way to do streaming iteration with a modern API. Who are transducers for? Well, and thereby, who is this talk for? Well, it's for people who want to do streamed data processing in Emacs. It's for people who perhaps aren't satisfied with the existing APIs, for example, the Seek API or some other common libraries that provide similar functionality. Maybe you're not a fan of the loop macro. Some people find it difficult to understand. Or maybe you've done a bunch of closure before, and you'd like more aspects of closure in your Emacs Lisp. Or maybe you're just interested in transducers in general, because the pattern has now been ported to multiple different Lisps. So I'm Colin. I'm Foskers on everything online, and I do mainly back-end programming work and a lot of open source software. I wrote Haskell for a long time, both as a hobbyist and professionally. Since the COVID years, I've been writing Rust, both open source and professionally, but now I find that in my spare time I'm mostly writing Common Lisp. Some things I learned from my years of Haskell was that a lot of programming is just altering the shape of data. Sometimes we work through our algorithm line by line. We're trying to just tell the computer exactly what to do. But if we step back, a lot of the time we're just getting in data of some shape, changing it, and then passing it along. And a lot of these patterns are common and identified, actually, decades ago. For instance, we have some collection, and we want to transform every element of that collection and then pass it on. Or maybe we're trying to filter out bad elements in that collection. Or maybe we're looking for a specific element in that collection. Yes, you could write all that with for loops, but these kind of common patterns were identified and given names decades ago. So why not use them? They say that there are two major problems in computer science, one being cache validation and the other being naming things. I've identified 5 other problems that come up when we're trying to deal with collections of data, or, big streams of data. So one is that, say if we were trying to, load a file all into memory all at once and process the whole thing, sometimes we can have memory problems. You've probably seen out-of-memory errors or such things. A second issue that comes up is that if we were looking at a giant for loop, in particular a nested for loop or such things, it can be hard to tell just by looking at the code what it's trying to do, what it intends. If we don't go character by character or line by line, it can be hard to understand it. Furthermore, and this is particularly an issue with Emacs Lisp, is that if one call, for instance, to seek map, then piped into seek filter, for instance, will have an intermediate allocation. The map will take the source container, allocate a new one, and then the filter will operate over the second one. This is wasteful. Furthermore, it can often be difficult to abort a stream. For instance, if we were filtering through our collection, but we knew we only wanted to go halfway, for instance, for some reason, we have no way to stop it halfway through. We just have to process the whole thing, even if we know we don't need to. And another issue is that for languages that have traits, or in Haskell they're called type classes, if you are defining what it means to, map over something, you often have to redefine that for every kind of container or thing that you're iterating over. Wouldn't it be nice if we could define things like map just once and then reuse them everywhere? Now, transducers solve all 5 of these without the addition of new language features and with little more than plain old function composition. So, if this is your first time hearing of transducers, no problem. They were originally invented in Clojure by Rich Hickey, and this is a quote from him. He thinks, "Transducers are a fundamental primitive that decouple critical logic from list or sequence processing. And if he had to do Clojure all over, he'd put them at the bottom, at the very bottom of all the fundamental primitives." Now, that's Rich speaking quite highly of them. And I think he has a point here. They were invented originally in Clojure, and in more recent years they were brought over to Scheme via Surfy 171. That's where I found them when I was learning the Guile language. In the process of submitting a patch, I realized that there were other things to be improved, so I ported the pattern to Common Lisp, then Fennel, and then more recently Emacs Lisp. The Common Lisp and Emacs Lisp APIs are identical, and the Fennel one is not identical but fairly similar. And overall, everywhere you find transducers, they should basically be fairly uniform. When I originally made the Common Lisp variant first, I sampled the APIs from a number of different languages and came up with what I believed to be a representative sample of what most people would want out of such a library. I gave functions their common modern names, so for instance, map is map and filter is filter, and so on. So, what does the usage of transducers looks like? Well, these examples will all be the Emacs Lisp variant, but the common Lisp will look basically exactly the same, minus this little T prefix. So, running transducers requires 3 things. It requires a source. This could be an obvious thing like a list or a vector, but it could be other things like a file, or in Emacs Lisp in particular, a buffer. A reducer is a function. It's something like the plus operator or the multiply operator, or certain constructors of various containers. It takes values and collates them into some final version. Now, finally, we have what we're calling here a transducer chain. This could be one transducer function, or it could be multiple composed together. And these are the functions that actually take data and transform them somehow. For instance, this. Okay, we have a list of 3 elements. We want to reduce it into a vector. And how we are going to transform the elements along the way, we are doing +1 to each of them. If this syntax is new to you, just know that this sharp quote just means that this thing that comes after it is the name of the function. Common Lisp and Emacs Lisp, this is necessary, but for Clojure and Scheme, it is not. So we can see here that just this example is, not much different than any other normal map call you might see made. But if nothing else, it's a handy way to, convert a list to a vector or anything else. There are many, many reducers available and many different forms that we can sort of collate the final value into. Let's see a more involved example. Okay, now we've got some more meat here. Here we can see usage of the comp function, and a custom source, ints. Ints is an infinite generator of integer values. So that's not like a list or a file. It will generate infinitely. Comp is letting us compose multiple transducer functions together. Notice that this is the opposite order of what we'd usually be used to from a function like comp. The order here is top to bottom, basically, so that the map goes first, then the filter, and then the take. So effectively, is what we're doing is taking all the integers that exist, positive, adding 1 to them, filtering out only the even ones, but then just taking 10. Cons here is a function that just produces the ending result as a list. So what happens here specifically is how we are avoiding intermediate allocations is first the number 0 will come through. It will be pulled out of this source internally by transduce. It will make its way into the map. The map will add it. Then it will immediately go into this filter step. So it's not like all the maps occur and then all the filters occur. We do everything for each element. So the 0 comes in. Now it's 1. The filter would occur. Well, it's going to fail that because it's not even, so it will just bail there. Now we'll go to the next one. Now 1 will come, it will become 2, then it will be saved by this even p call, and then the take will capture it because we only want 10 values here. And you can see 2, 4, 6, 8, and so on is the result that we expect. So let's play around a little bit. Let's jump into Emacs and see what we can do. All right. You should see my Emacs screen here. These are the actual notes for the actual presentation done in org mode. So I'll boost that up in size for a little bit. That should be more than big enough for you. Well, just by changing the reducer, we can change the result. Okay, now it's a vector. Well, what else can we do to it? Well, let's just add up the results. Maybe we just want to count the results. Oh, indeed, there were 10. What if we want to find the average of the results? What if we want to find the median of the results? And so on. Here's some more interesting things that we could do. We could add different steps. So here we have all the integers. Let's add, okay, we'll keep that. We're gonna add t-enumerate. What enumerate does is it adds, well, for each item that comes through, it is going to add a sort of index to it and make it a pair. So in this case, it's going to be equal to what came in here. Well, we can change it. If we start this at, say, 1, now it will be different. So 1 will be paired with 0, and then 2 would be paired with 1, and so on. Well, except that the even call will change that a little bit. But why we're doing this is because we want to form a hash table. Let's move that down to 3. Maybe we'll get a better result. What do we see? Okay, here now the result is a hash table. What are its values? Well, 0 seems to have, the key of 0 seems to be paired with 2, the key of 1 seems to be paired with 4, and 2 seems to be paired with 6. Well, maybe let's jazz that up even a little bit more. We're going to start from a string and we'll call it hello. That's not going to work anymore, and neither is that, but what we could do is we could say tmap string, I believe we'll do that. Let's see if that works. It did, so that's going to convert a character into a string. Let's just go 2 just to make it a little easier. Okay, now you can see that we've constructed a hash table here. The key of 0 is mapped to the string of h, and 1 is mapped to e. Now, I really like having this reducer in particular, and know that hash tables are also legal sources. I find that both in Emacs Lisp and in Common Lisp, dealing with hash tables, like creating them and altering them, can be a bit of a pain. So having them immediately available like this with transducers is very handy, I find. We can work with something that wasn't a hash table. We can construct it in a way that makes it amenable to that, and then reduce it down into a hash table, and here you go. Very handy. one last point is that you can see sort of very clearly what this is attempting to do, as opposed to, say, a for loop. You know, it's very clear what that step is doing, and then you can see what that is doing, and you know that the result is going to be 2. Each line is kind of its own declarative step, and it should be clear, just by staring at this, basically what you're going to get out. This is one main difference from other languages that have things, say, for instance, Rust's iterator API, is the difference between sort of the transducers and the reducers. Pardon me, if we go up here, for example, like the difference between the transducers and the reducers and the sources is not explicitly laid out, whereas with transducers, it is. You have to be aware of how these things are different, and I think that helps clarity. Moving on, how transducers work. Well, we want to go see the README. So what we're going to do is we're going to go to, let's go over here, see how transducers. You should still be able to see this. So this is the CL example. Actually, let's go to transducers.el. Their APIs and READMEs are the same, but just for the sake of it, we will go see how this looks on the Emacs side, just so that's nothing is a surprise. But recall that the APIs are essentially the same between the two. So if you go to this section, writing your own primitives, you can read about how transducers are actually formed, whether or not you want to write them yourself or not. So we can see here, tmap, okay, we accept, the function that you want to operate with, and then you've got this extra little lambda here that's coming in, and it's receiving a thing that is named reducer. Now, while here we're calling it reducer, it's actually the chain of all the composed functions together. So it's all those main transducer steps, and finally it's the reducer all composed together with normal function composition, and that will matter very soon. Now here's the actual meat. We can see the accumulative result that's coming in with the current element, and now we need to operate on this. Where at normally map, we would see us applying, the F to the input, but here you can see us applying the F to the input and then continuing on. So us calling the rest of the composed chain here is the effect of, in the previous slide, moving to the next step. We could ignore this line for now. If you're curious, please read the README in detail. Now, what about reducers? What do those look like? Well, let's just scroll down here. So recall that a reducer is a function that's consuming a stream, right? Zoom that up for you a little bit. Now, in the case of count, sort of recall that this is how it's working, how we saw a moment ago. So clearly this list of 5 elements only has 5 things in it. Well, a reducer by structure is a function of 2, 1, or 0 arguments. So we can see here in the case of 2, this is the normal iterative case. We don't care about the input for count. We just care about the current accumulated, count that we're doing, and we add 1 to it, and that's it. This then goes back sort of to the loop, and the whole process starts again with the next element. In this kind of done case, this is used internal to that sort of the supervising function transduce. It's just confirming the final result. Sometimes some post-processing is necessary here, but in the case of count, as it is so simple, that is not necessary. And now here's the base case. This is also used within that supervising transduce function at the very top. Well, if you're counting, you have to start from somewhere, right? So in this case, well, what you're starting with is 0. In the case of cons, you'd be starting with an empty list. In the case of vector, you'd be starting with an empty vector, and so on. And once again, if you are more curious, please take a look at the README. Okay, transducers in the wild. Well, let's go take a look at processing some CSV data. We'll just go down here. We're going to open up a new Emacs Lisp bracket here. So I have a file, and in this file, let's just go look at CXB right there. You will see that we've got some bank transaction information, and it's got these transactions from a whole bunch of different people into different accounts, and whether it's money coming in or money going out, and then a basic description. How's your Latin? But for this little test, what we want to do is we want to find Bob's final bank balance. Well, let's get onto it. We can, first of all, let's just confirm. Let's do some basic stuff. So with current buffer find file no select, and then what's the name of that file? This is pre-organized, so you will just see it right here. T transduce and T comp. We don't know what we're going to comp yet. Actually, I'll just pass to show you, and then we will see. Let's just do a little T count just to confirm. What's our source? Well, our source is a buffer. T buffer read. And note that because we're using with current buffer, if we go like this, if we go current buffer, this will just work. So now well, that was odd. I shouldn't have done like that. There we go. So that should make that a little smaller so you can see what it is. Now if we hit enter, we should get the right result. Okay, so there are 50,001 lines in this file. The one extra one is the name of the headers, right? But we want to process this file in more detail. So how can we do that? Well, let's start by just automatically interpreting the results as CSV. If we do that, okay, well now we only have 50,000 entries as we expected, right? Because it's going to pull out the header line. If we now say we want to just filter out, we only want Bob, right? So if get hash, it was in the row of name, and so each line here is made into, at least by default, is made into a hash map. So if we go like this, we should see that, okay, so 12,000 of these lines, or thereabout, belong to Bob. Let's just move that over a little bit. Actually, I suppose we don't even need that anymore. I'll just keep that full size for you. Okay, so all right, there's about 12,000 results of for Bob of the 50,000. What's next? Well, we want to confirm. We want to pull out everything that all of the in and the out entries. Thank you. So, string to number, because we know that everything came in as strings, unfortunately. The from CSV doesn't try to be smart at all. It's just pulling everything in as string values, and then if you want actual things to be numbers or whatever, that is up to you to do the parsing yourself. Okay, so we have those two values now. And we know that, we saw from the data just a moment ago that you're only going to have a value in one column or the other. It's either going to be 0 in the empty one, or you're going to have some number in the other. So we know that we can just naively add them. If it was in, it would always be positive, so we'll just add that. But in the negative case, we want to just make it negative really briefly before we add them all together. Let's now just prove to ourselves that we are sane here. What we're going to do is we're going to quickly go say, take 5 just to convince ourselves. And then we'll go cons. And let's see if we get kind of results that make sense. Okay, these sort of make sense. It looks like, Bob's got some big expenses here. If we take, say, 15, does it look any better? Okay, looks like he had a payday. All right, good job, Bob. Let's get back in there. And now we only really care about adding the final result, right? So there we go. Add that all together, and we'll see what we get in a moment. Okay, wow, Bob's rich. Okay, so it looks like in his 12,000 transaction, Bob has an overall net worth of $8.5 million. Looking pretty good. So here's an example of how you can, particularly in Emacs Lisp, how you can very easily just get a file, consider it the current buffer, and then just do whatever you want to it. Note that there is sort of first-class support for both CSV and JSON, and then you have, and both of those bring in their values as hash maps, and then you're just free to do whatever you want and process them, potentially both writing them back out as CSV or JSON once again. Okay, so some issues with transducers that can come up is that 1, a zip operator is missing, but I'm working on it. 2 is that performance, particularly in Emacs Lisp, isn't that great. It could be due to the sort of nested Lambda calls that have to occur internally, but the common Lisp implementation is quite good. And there's yet no support for parallelism. You can imagine that a lot of those steps you could potentially perform in parallel depending on the platform, but sort of research has not yet gotten that far. Okay, that's all. Thank you very much. If you have any questions, please contact me.